Swayam Prabha. Digital India. Educated India.
Right. So today's topic is transportation problem special cases. Within the special cases, what we are going to discuss mainly the maximization problems, how to solve maximization, because we know that transportation problem is defined for minimization. But suppose we have a maximization problem, then how do I go about? And the second thing we shall discuss is some special cases where particularly that demand has a variability. Is it all right? So if there are variable demand, then what kind of situation can occur? And thirdly, a little glimpse of aggregate planning I shall give you so that a general broad idea can be formed. Right. So first of all, let us look at the maximization problem. Now, in this particular problem is familiar with you because we have solved this problem for minimization, and various other variations also we have solved where the availability is more than demand or demand is more than availability. And thereafter, we had also seen if there are some restrictions of certain factory not able to send material to certain warehouses. So all these different cases we have already seen. So first of all, this is a balance problem. So if it is not a balance problem in case of maximization, we have to balance it first. So this is one thing, that is the first. And then first of all, these computing Cij minus Zij by the UV method, that for the basic variables ui plus vj equal to Cij, and there will be m plus n minus 1 basic variables, and for the non-basic variables it should be Cij minus ui plus vj. All these rules remain intact, so there is no change in all these rules. And you will be surprised to know that even the Vogel coefficient rules are also going to be the same. So let us look at the Vogel approximation method once again. Determine the minimum penalties for not utilizing the best possible cell for all the rows and all the columns. So what I said, that irrespective of whether the problem is of minimization or maximization, the Vogel's approximation method rules are going to be the same. Only the interpretations are going to be different. So what is different in case of maximization problem? Read the first step and can you tell me where we are different in case of maximization? Please read the rule number 1. Determine the minimum penalties for not utilizing the best possible cells for all the rows and all the columns. Right? So what is different in maximization problem? For utilizing the best possible cell, the best possible cell is no more the lowest value in a row or in a column. The best possible cell is the highest value in a row or a column. So what we have to do is we have to take the highest value and the next highest value and take the difference, and that is the minimum penalty. All right, so this step is the same, but interpretation is different in case of maximization. Thereafter, obviously, they avoid incurring the maximum of these minimum penalties by allocating the maximum possible amount in a suitable cell. Suitable cell here is nothing but the best possible cell in that row or that column. Now cross out row I and column j as the case may be and reduce the corresponding availability and demand by the amount assigned. Repeat the step till m bar plus n minus 1 basic variables are obtained. So basically Vogel's method is to find out an good initial solution. So that's what the Vogel's method does, right? So let us calculate the minimum penalties for this particular problem. So you see, as you see in the first row, best possible cell is 25. Next best is 21. So therefore the minimum penalty is 4. In the second row, the best is 23. Next best is 18. So gap is 5. Here the best is 41. next best is 32, so gap is 9. Here 32 minus 21, so 11. 27 minus 18, so 9. 25 minus 18, 7. And 41 minus 23, 18. So which one is the maximum of these minimum penalties? So clear, it is 18, is it not? So where do we allocate? Which cell are we going to choose to allocate? Please think over. So if we maximum of the penalty is 18, that means this column is chosen. Now if this column is chosen, which cell is going to be our choice for allocating materials? So it should be F3 W4, because 41 is the highest and it's a maximization problem. So we should allocate as much as possible in this particular square. And how much is that value? That value should be 15, because 15 is row wise, column wise, and 19 is row wise, 15 is lower. So maximum that we can allocate here is 15. Good. So that is how we have allocated 15. And after allocating 15, we put the demand of W4 is now satisfied, and the availability of F3 is now reduced to 4. Now, once again, the penalties are recomputed. Obviously, for these columns, no change, and these 18 will be crossed now. And for this side, they are now stands to be revised. So what should be the revision? The revision is 25 minus 21, 4, 18 minus 17. So it should be 1. And this one, 32 minus 27, this should be 5. Right? So this should be 5, this should be 1, this 4 should remain, and these 3 unchanged, 18 should be crossed. So that is how the new minimum penalties are there, and those are now calculated. Is it not? 4, 1, 5, and 11, 9, and 7. So after recomputing the penalties, again we see the maximum is 11. So obviously we have to choose this particular column. And in this column, the maximum value is 32. Column wise total is 6, row wise total is 4. So only 4 can be allocated. So this 4 is now allocated. And after allocating 4, this 4 is gone and this 6 is revised to 2. All right, so now we have only these many cells, and recomputing the penalty, this becomes 1, this becomes 4, because 25 minus 21, this becomes not 11, this will now change to 4, 21 minus 17, so it should become 4, and this should become 2, and this should become 11. All right, so these new penalties will be obtained next. So these are changed, and again we find 11 as the highest. So if 11 is highest, so 25 is the best possible square in this particular column. So we can enter in 25 some value. So what should be that value? That value should be the row wise total is 11, availability, column wise demand is 12. So 11 is lowest, so 11 here. All right, so that is very clear now. So we enter 11 in this particular square, and after we have entered this, now the problem has become trivial, because only one row is remaining, and we have no choice but to fill up the remaining amount, because only these 3 cells are available, nothing else is available. So this column total must match. So here we must enter 2. All right, so let us enter it 2 here. So a 2 has to be entered here. There is no other choice. All right, now this F2 W2, how much we have to enter? Tell me the value that must go here, because we have 13 available row wise and 10 available column wise, so only 10 can be entered here. So after entering these 10, where is the cursor? Yeah, so cursor is here. So this 10 we cross, and these then how much we can enter in the last one? We can enter a 1. All right, so 2, 10 and 1, that should be the entry. And after all these entry, this 13 is crossed and this 2 is also crossed. So all are crossed and we have now got how many entries? 3 plus 4, 1, 2, 3 plus 4, 7 minus 1. So 6 entries should be there. So 1, 2, 3, 4, 5, 6 entries are there. All right, so that means we have got a good initial solution, right? So, and good initial solution has already been obtained, so that we can call our basic feasible solution. So this is where the basic feasible solution is shown, and this basic feasible solution is obtained with the application of VAM. All right, so that's the first part. Now, after this first part is done, then we have to begin our transportation algorithm by UV method, and we have to compute the Cij minus Zij values. So here are the UVs. So assume we put 0, U2 equal to 0 in this. Let's take the pen. So let us say that put this 0. So when we put this 0, then we can compute this 17. We can compute this 18. And we can compute this 14, right? So these are to be computed. Now, once this 14 is obtained and we know this is 25, so using them, we can compute this U1 equal to 11. All right, so this is to be computed. And then because this is 17 and this is 32, so we can obtain this 15. All right, so now these 15 and this 41. So these 15 and 41, so this 26 can also be obtained. So you see now the sequence is shown to you. The sequence is we have this 0. Using this 0, we get this 17. Using this 0, we get this 18. Using this 0, we get this 14. Using this 14, we get this 11. And using this 17, we get this 15. And using this 15, we get this 26. All right, so this is the calculation. Then comes the validation, a cross check. Cross check is must. So 11 plus 14 is 25. 0 plus 17 is 17. So for all the basic variables, Ui plus Vj should be equal to Cij. So 0 plus 18 is 18. 0 plus 14 is 14. 15 plus 17 is 32. And 15 plus 26 is 41. So all are checked. And then what we have to do, we have to compute the Cij minus Zij, which is this Cij minus Ui minus Vj. So 21 minus 11 minus 17, so minus. 16 minus 11 minus 18, minus. 13 minus 11 minus 26, minus. 23 minus 0 minus 26, minus 3, so minus. 27 minus 15 minus 18, so minus 6, so minus. 18 minus 15 minus 14, so minus 11, so minus. So what we find that all the 1, 2, 3, 4, 5, 6 non-basic cells are returning negative Cij minus Zij value. And this is a maximization problem. So therefore, we can say that this table is also our optimal table and this is our optimal solution. All right, so this is how the optimal solution could be obtained. We are fortunate that we did not have to do many iterations. The basic feasible solution returned by the Vogel's method is also optimal. So the optimal total profit can be counted also, that is 25 into 11, 17 into 2, 18 into 10, 14 into 1, 32 into 4 and 41 into 15. So that gives us 1246. All right, so this is how maximization problems are solved by making use of the same algorithm. Basically, you see, only thing that we have to different is that the interpretation is best possible cell and next best possible cell, and then the Vogel's method remains the same. And when it comes to the transportation algorithm, then Cij minus Zij value, when they are all negative, the problem is optimal. I hope you have understood. Anyhow, we are also taking one more problem. Okay, once again, this problem you follow once again, this will be clear because this is also a maximization problem. And here also we shall calculate the penalties once again. So you will be more clear. All right, so this will be repeat of the same thing once again in a different problem. Right. Now, so far we have seen transportation problem where the demand of the warehouses or the destinations are constant. We shall now deal with an example where the demand of the warehouses are variable. Even then, some of the warehouses may be having a committed demand. This means that this much amount cannot be sent from a dummy factory. Additionally, some other or some already having a committed demand warehouses may be interested in as many as possible of the remaining units. So what happens that two kind of things can happen. One thing could be that there is a committed demand. That means that much demand has to be met. That means you cannot take the opportunity of sending from a dummy factory, in a sense not send at all. That means that much has to be sent. So this is the committed part. Then there could be some warehouses amongst them who have a committed demand, or some other warehouses that do not have a committed demand. They may have a condition that they are interested as many as possible of the remaining units. Let us see what does it mean. So here is a problem, variable demand problem. So how to transport materials from the 3 factories to the 4 warehouses so as to maximize profit. Please note the values in red are unit profits for transportation and the problem is one of maximization. So these are unit profits and the problem is one of maximization. Now these are the availabilities for the 3 factories. Factory 1, 3000, factory 2, 5000, factory 3, 4000. So what is the total availability? 12,000. And what is the total demand? See, the demand is interesting. W1 has got 4,000 committed. 3,000 committed is the demand for W2. W3 has 1,000 committed and W4 has none committed. But there is an additional thing. Additionally, W3 and W4 are interested in as many as possible of the remaining units. How many are the remaining units? 4,000. Is it not? Total availability is 3 plus 5 plus 4, 8,000. Total demand is 4 plus 3 plus 1, 8,000. So 4,000 is the additional available units. Now what to do with those 4,000? W3 and W4 wants as many as of those. That means if 4,000 is available, W3 is interested in all of 4,000. W4 is also interested in all of 4,000. But since we have only 4,000, we cannot give to both, is it not? That is not possible. So this is the difficulty. So how to solve this maximization problem? Do we need a dummy factory or a dummy warehouse or both? What do we do? Should we take a dummy factory or should we take a dummy warehouse? So think and tell me. Just think for a minute and then tell me, should we require a dummy factory or a dummy warehouse or both? Because in this case, availability is 8,000, demand is, availability is 12,000, committed demand is 8,000, but there is also demand of W3 and W4 as many as possible of the remaining units. So you cannot say that total demand is 8,000. Total demand is as many as possible for W3, W4 of the remaining units. So do we need a dummy factory or a dummy warehouse or both? Some answer you give. So yeah, apparently it looks that, these if we have a dummy warehouse, but then you see already W3 and W4, they are interested in the remaining units. So which unit should go to the dummy warehouse? What should be the demand of the dummy warehouse? If you put 4,000 as the demand of the dummy warehouse and solve the problem, This means that the remaining units are not going to be given to W3 or W4. They will be given to the dummy warehouse. But that's not correct, is it not? That's not correct. Suppose you solve it with W1 4000, W2 3000, W3 1000, remove W4 because it has non-committed, and you have instead a dummy warehouse with 4000. Then maybe the solution would be 4000 here, 3000 here, 1000 here, and 4000 with the dummy warehouse. But that doesn't solve the problem because W3 and W4 were interested in the remaining units. So you see, there is a fallacy. Now, do we divide the problem into a number of sub-problems? In that case, it will not remain a transportation problem. So there are if-then conditions. Can we accommodate them in the solution logic? If we try that, we shall lose the simplicity of the transportation problem because transportation problem cannot accommodate if-then logic. But we do not know exactly how much we should supply to the warehouses W3 and W4 who would like to have as many as possible of the remaining units. So these are the issues. These are the issues in this particular problem. Now let us say what we know about the problem. W1 and W2 and W3 have committed demand. They cannot be served from a dummy factory for the committed part. W3 and W4 want as many as possible of the remaining units. However, these demands cannot be met from a dummy factory. All right. W3 seems to be common in both committed demand that cannot be supplied from dummy and in obtaining remaining demand that cannot be that can be supplied from dummy. So now this much we know. All right. So tell me now. Tell me what should be done. What should we do so that we can still solve the problem by the transportation logic, and we don't have to really, use the if then else rules, or we don't have to divide the problem into two different parts, etc., because they don't work. Those logic is not going to help us. Okay, is there a comment? So we'll see that. But first of all, can you see that W3 seems to be common in both committed demand that cannot be made from the dummy. So W3 has got two parts actually. One is the committed part. Another is, as much as the remaining units. So suppose we add a dummy factory. So if we add a dummy factory, what should be its availability? We know that W1, W3 have a committed demand. They cannot be served from a dummy factory for the committed part. Again, W3, W4, as many as possible of the remaining units, and W3 seems to be a common in both of the conditions above. So way to go is, suppose you split W3 into two warehouses, right? Let us split W3 into two warehouses, W3C and W3N. So if you split it into two different warehouses, so now we have W1, W2 and W3C having committed demand. They cannot be served from a dummy factory. And W3N and W4 wants as many as possible of the remaining units. However, these demands cannot be made from a dummy factory. So the problem related to W3 being common to both of the conditions above is now sorted out. All right, so this is the problem. So the problem is now that we have a dummy factory. This dummy factory, we don't know what should be the cost units. And here is the availability. So this is the availability 3000, 5000 and 4000. We don't know the availability of FD. We know that committed stock, committed demand for W1, W2 and W3C, that means the committed part of W3, are 4000, 3000 and 1000. So what should be the demand of W3N and W4 and what should be the availability of FD. You have made a very good comment that give them as much as possible. All right. So if you take that kind of a strategy, you see this is a very interesting and good strategy. The strategy is that W3N is interested in all the remaining units. How many are remaining units? 3000 plus 5000 plus 4000, that is 12,000, minus 4000 minus 3000 minus 1000 equal to 4000. So let us give W3N 4000. Let us also give W4 4000. All right. So if we give them as much as possible, that is what they want. All right. So the total demand then become 16,000. That means 12,000 is available. Remaining 4,000 should be supplied for dummy. Now let the problem decide that whether W3N and W4 who gets from a real warehouse and who gets from a dummy warehouse. So basically the dummy warehouse part is not meaningful because that amount is actually not getting supplied. So if out of the remaining 4,000 units which cannot be supplied for dummy, which has to be given to W3N or W4, that should be coming from the real warehouses. So basically what is going to happen? 4,000 is going to come from real warehouse, 4,000 is going to come from dummy warehouse, but who gets dummy warehouse material and who gets real warehouse material, that would be actually decided by the problem itself. So what will happen? The problem will decide whether how these remaining 4,000 units will be divided between W3N and W4. All right, so with that discussion, now tell me what should be the demand of W3N? What should be the demand of W3N? And demand of W4? That also should be 4,000. Availability of FD should be 4,000 and total would be balanced in both sides, that is 16,000. Is it all right? And here is the cost part, because FD cannot send to W1, W2 or W3C. So that should be minus M because it's a maximization problem. All right, because it is maximization problem. So FD to W1, FD to W2 and FD to W3 should be minus M. Is it clear? So because of that, we can make a conclusion that FD to W1 cost should be minus M, minus M and minus M, and 0 and 0 for the non-committed part. All right. So that is the cost details, and here are the demand and the availability details. So that now we have a balance problem which has 4 factories. One of them is a dummy, and there are 5 warehouses. So 4 plus 5 minus 1, we shall have 8 basic entries, and it's a balance problem. So now we have the transportation network the transportation matrix, which we shall solve. First of all, we shall use the Vogel's method to get a good initial solution, and then after obtaining the solution from Vogel's method, then we shall go ahead with the transportation algorithm and try to find the final solution. So that part is more known to you. So let us go ahead and solve the problem. This will also give a quick revision of the penalties. So initially, I have not allocated these 3,000. So that means this cross and these values are not there. So let us compute the penalty. In this row, once again, please here, if you have not understood the minimum penalties. So this is a maximization problem. So this is the best possible square in this particular row. Next best possible score, profit is 64. Unit profit is 64. So 65 minus 64, minimum penalty is 1. In this particular row, 68 is the best possible square and 67 is next best possible square. So we get 1. Here it is 63 minus 60, so 3. Here it is 0 minus 0, so 0. Here it is 68 minus 65, 3. 67 minus 63, so that should be 4, not 7. Anyhow, that's a mistake, so it should be 4. And thereafter, 65 minus 62, it should be 3. 65 minus 2 is 3, and 64 minus 62 is 2. So highest possible value is this. It is not 7, it should be 4. So we make entry here. The base square is 67, so the value that can go is 3000. So we make an entry of 3000 here, and in this row we simply cross this 5000 and get 2000. So this is the first entry. Now after first entry, then comes the second. So we revise the penalties again, and this time we see a series of 3s, and then we choose one of the 3s, and then we see that this is the best possible square. So we make an entry of 2000, and then this 2000 is crossed, and this 4000 becomes 2000. So at the third stage, again, we get a series of 3s. In fact, no, there is 1 4 we get here, because this 62 is gone, so it becomes 4. So entry is here. So we make an entry of 3000 and cross this availability, and this availability is then 1000. All right. So this is the 3 entries have been made. At the fourth level, this time again, penalties are various penalties are obtained, and at this time we have an M. Because we have an M, so we make an entry of 2000 here. All right. So like this we continue. You go through the problem carefully so that you understand. I'm not going into nitty-gritty because we have already calculated this VAM many times in a number of problems. And next entry becomes 1000. So then we have this situation. So we have already said that there should be 8. 1, 2, 3, 4. 1, 2, 3, 4, 5. 4 plus 5 minus 1. There should be 8 entries. And so far we have only 1, 2, 3, 4, 5 entries only. Isn't it? So 3 more entries have to be made in these squares. So that is the situation. So next is these 1000. So 2 more are there, and then it becomes trivial. Look here, when we made this entry of 1000, again row and column get satisfied simultaneously. So we satisfy the row. That means the column is still not satisfied, and we get a 0 here. That means this problem is also degenerate, right? So there is degeneracy. So degeneracy is also there in this particular problem, and we have to put a 0 somewhere, and only 1 square, only 2 squares are left. So we have no other option but to enter a 0 here and a 4000 here. All right, so we make those entries, and then we get the basic feasible solution. So look here, this is our basic feasible solution, and this particular basic feasible solution is having 3000, 2000, 3000, 2000, 1000, 1000, 4000 and 0, and there are 8 basic variables. All right, so next we have to see that whether this particular basic feasible solution is optimal or not. Now, how to check optimality? We have to then UV coefficients we have to put, and after putting the UV coefficients, then we have to see the Cij minus Zij value. So we start with this U3 equal to 0. That would give, this 63, because this is 63. That 63 would give a 5 here because of this 68. Now this 5 would give a 62 here because this is 67. That 0 would give a 59 here, and that 0 would give a 60 here. This 60 would give a 4 here. All right, so almost everything we are getting. Now we have already got this 60 and this 0. So this 60 and 0 would give a minus 60 here, and these minus 60 and 0 would give a 60 here. Thereafter, after we calculate the Cij minus Zij values, because 65 minus 4 minus 63 is minus, so many of them are minus, but 2 of the squares, you see, one is plus 1, another is 0. So this square is a good square. So we have to make an entry here. So if we increase here, how the closure is obtained? How the closure is obtained? So F2W3C goes up. Let us put that with a pen. So suppose this square goes up. Now which one should go down? Yes, F3W3C, that should go down. Now if this goes down, then the good way of having is this should be going up and this should be going down. All right, so now we have been able to find the closure, and once we find the closure, then which is the minimum unit that is going down? That is 1000. Is it all right? So what will happen? An entry of 1000 could be made in this particular square. An entry of 1000 can be made in this particular square. This would become, it should go away. This 2000 will become 3000 and this 2000 will become 1000. Right, so precisely this is what is shown here. If it goes up, this goes down, this goes up and this goes down. So we have a closure and then we make some entry at F2W3C. Right, we make some entry at F2W3C. So when we make that entry of 1000, this is going to be our new solution. So this new solution, again, we recompute the UV coefficients. If this is 0, this is 63. If this is 0, this is 60. This is 60, this is 4. This is 60, this is minus 60. This is minus 60, this is 60. And here we got 0, so 63, 63, and there we got 5. Using the 5, we can write 62 and 60. Because interestingly, there is not much change in the UV coefficients. I think little change has happened, that 59 has become 60. So anyhow, now, when we recompute, we find all the Cij minus Zij is negative, excepting the F2W3N where it is 0. So look here, somebody has asked me a question that can a degenerate solution also have alternate optimal solution. So here is an example. Degenerate solution, because there is a 0 here. So that degenerate solution, not only it is degenerate, but also there is alternate optimal solution. Because of this 0, this particular solution is definitely optimal, but we also have a 0 in the Cij minus Zij. Therefore, not only this is optimal, but an alternate optimal solution also exists. So what is that alternate optimal solution? Let us see that. So, if we make some entry here, we have to find a closure. So obviously we have to take these down and we have to take these up. Now, if you take these up, then this has to go down. And if this goes down, then this has to go up. This has to go up, this has to go down. Now, you see, this is very interesting. You see, what is interesting here is that, what is interesting here is that, these going up is a 0. So this will become lowest value that to go down is 1000, right? So lowest value to go down is 1000. Let's go to the next slide where we have shown this. See, lowest value to go down is 1000, but there is a tie there, and that tie is 1000 and 1000. So if both goes down and both you put to cross, then we are not going to have the required number of basic feasible solutions. So you have to retain one of them. You cannot simply make both as 0. See, when in a particular these operation and you find that two variables are going down simultaneously, you cannot make both as cross. You cannot make two variables going away, going to non-basic, and one variable comes to basics. So what happens? This variable comes to the basis, and one of these two has to go away to non-basic. right? It has to be a single exchange and not one in and two out. You cannot have two out, so that is not possible. So one of them has to go out, the other one has to be retained with a 0. Now, which one you want to retain, that is your choice. Now, suppose we take, let it go away and maybe retain these as 0. So what is really happening that, this 0 becomes 1000 definitely. So look here, that is our final solution, that 3000, 3000, 1000, 1000, 4000, but this 0 is retained. All right, and this 0, which was earlier was 0, so that becomes now 1000. Is it all right? So this is what is the alternate optimal solution. And look here, this is also degenerate because there is a 0 here. And this 0 indicates that from this alternate optimal solution, again, you can go back to the original optimal solution. Now look here, what does this solution means? What this solution means is that additional 4000 units are to be divided in this manner. In which manner? 1000 should go from F2 to W3N and 3000 should go from F1 to W4. Is it all right? That means it is divided into 1000, 3000, that ratio, right? In that ratio, it is divided. The remaining units which they want will be served by dummy. But if you look at the original optimal solution, the original optimal solution was saying that don't send anything to W3, send entire 4000 to W4. Is it not? That is more profitable. That is, F1 should send to W4 3000 units and F3 should also send to W4 1000 units. So these alternate solutions have different meaning. These alternate solution means that W3 gets only 1000 in the committed part. Remaining 4000 that it wants should be served by dummy. That means it doesn't get, right? The 4000 units will be going to W4, 3000 will be served by F1 and 1000 will be served by F3. And in the alternate solution, what it means is that out of the committed stock, W3 gets 1000. The remaining 4000 units will be divided in this manner. W3N will get 1000 and W4 will get 3000. All right, so this is how, these kind of problems are to be solved. And we have to be very careful in understanding the logic. And therefore, thereafter, we have to think how to solve this. So before I move over, is there any question? Okay. Right, so let's move over very quickly. What I should do in the next 10 minutes or so, we shall take up an aggregate planning problem. And this one, I am not going to go in deep. I'll just, today, because we don't have much time, we are just going to give you a glimpse of the broad idea of these kind of problems. So what happens that the manufacturing capacity of the blow-cool air cooler plant is less during autumn and winter as the company diverts part of its capacity to the production of geysers and water heaters. The estimated capacity and demand figures for the cooler is shown below. So manufacturing capacity in autumn 12,000, demand is 10,000, winter 8,000 and 5,000, spring 20,000 and 25,000, summer 20,000 and 40,000. The selling price of the cooler is fixed at rupees 10,000 per unit, but in order to promote the sales during off-season, the company offers a discount of 20% during winter and 10% during autumn. The production cost of a cooler is rupees 6,000. A subcontractor is willing to supply any number of these coolers to the plant in any quarter at a cost of rupees 9,000 per unit. Also, excess production of any quarter can be stored for sale in a future quarter at an additional cost of rupees 1,000 per cooler per quarter. Work out the optimal strategy for the company to meet the demand. So look here, in this particular problem, it is the company that has to come out with its production schedule. And here the demand is at different quarters. Is it not? The demand is therefore time based and not actually the place based. So you see both sides we have autumn, winter, spring and summer, and here also we have the the subcontractor, and here the available, I'm sorry, these are the availabilities, and these are the demands in autumn, demand in winter, demand in spring, demand in summer. So, the what is the autumn demand? 10,000, winter demand 5,000, spring demand 25,000, and demand 40,000. And what are the availabilities in autumn? 12,000, winter 8,000, spring 20,000, and summer 20,000. So these total is 60,000. These total is 80,000. Now, since the subcontractor doesn't give much profit, because subcontractor is asking for 10,000 rupees per unit. If you see, they are asking 9,000 per unit. So if 10,000 is selling price, only 1,000 profit is obtained. On the other hand, the production cost is only 6,000. So it is not very good to get from the subcontractor. So therefore, the subcontractor can supply at any unit. So we only 20,000 we would like to take from the subcontractor. That is the remaining unit. So the total becomes 80,000 from both sides, and we have a balance problem. Now, these colored squares are very important. You see, if you produce in autumn, supply in autumn. Produce in winter, supply in winter. Produce in spring, supply in spring. Produce in summer, supply in summer. So those costs are computed. I'm not going into detail based on the discounts and other things. Say, for example, in autumn, production cost is 10,000 and production cost is 6,000. Sale is at 10,000. So it should be 4,000 profit. But there is a 10% discount. So 1,000 discount is gone. So we have 3,000 only. Anyhow, so like these, the costs are computed and the profits. So these are the profits after taking the selling price and the production price. So these are the different values. Now what happens? Suppose you produce in autumn and sell in winter. Definitely the profit margin is going down, because not only we are have to pay the prices, the discounts and all those things, but additionally you also have to bear the inventory cost. You see, there is an inventory cost. Excess production of any quarter can be stored for sale in a future quarter at an additional cost of rupees 1,000 per cooler per quarter. So there is an additional cost of inventory, and that is, if you produce in autumn and sell in winter, then 1,000. If you produce in autumn and sell in spring, then 2,000. If you produce in autumn and sell in summer, then 3,000. So like this, it goes up. But the costs are, the profits are varying because of different calculations of discounts and other things. So like these, we have all these different figures, and you see this side is called back ordering. This is the other side, that produce in winter, sell in autumn. Now you may be thinking that autumn is before winter. How can I produce in winter and sell in autumn? That is called back ordering. Basically, when the autumn was there, you are not selling anything. You are saying, look here, I cannot supply you now. Wait for 1 month, and then the supply will be made. So obviously it has a cost, because the customer has to wait for a 1 month. Is it all right? So we are assuming that there is no back ordering. So since no back ordering, all these figures are minus M. All right. So that is how the matrix is made, and there is this back ordering sales, and there is this inventory carrying sales. There is also subcontracting options, and then we have this particular matrix. And in short, these are called the aggregate planning problems. So thereafter, the VAM basic feasible solution is shown here. So this is our VAM basic feasible solution. This particular basic feasible solution is also degenerate. See, there are 1, 2, 3, 4, 5, and 4. So there should be 8 entries. So 1, 2, 3, 4, 5, 6, 7. So a 0 has been put, and these are the 8 different entries in this basic feasible solution. All right. So this is the first. So you see one very interesting thing you see that instead of using VAM, even if you would have used northwest corner rule, you would be getting a reasonably good solution, because this is the nature of the problem, that as you go down, it is the diagonal which is the most lucrative, because if you produce in autumn and sell in autumn, that is always going to be a good choice. All right, so the long diagonal is good, and some of these, like this square also, you see cost is quite less. So like these, the northwest corner rule sometimes even give a very, very good solution in aggregate planning kind of problems. And that is probably the reason which I said in the very first class, that northwest corner rule has become a popular rule to use in getting a quick initial solution. So after we get the VAM basic feasible solution, then the UV coefficients are computed. And after we find the UV coefficient, we find yes, it is optimal. Although there is a 0, that 0 means there is an alternate optimal solution. So this iteration 1 is obtained, and therefore we find that this is optimal. And although it is optimal, there is also an alternate optimal solution. So if something goes up here, this goes down, this goes up, and this goes up, this goes down, this goes up, and this goes down. So minimum to go down is 2000. That means this 2000 will come here. So that is an alternate optimal solution is also available in this particular problem. Right, so that's a quick take on the aggregate planning problem. And there is consideration of back ordering, there is consideration of inventory carrying cost, and there could be different other costs. The essential idea is how much should be produced in which month and how. All right, so that is the basic idea of this alternate optimal solution. All right, so this is how we solve this kind of problem. And let us conclude here for this particular class. So thank you very much.